The origin of the Earth's magnetic field. The Earth's core is considered to be responsible for the origin of the magnetic field. The crust of the Earth cannot support a dipole field as at about 20 km depth where the temperature reaches about 600 degrees Celsius, which is called Curie temperature. The ferromagnetic minerals lose their property of spontaneous magnetization at this depth. Therefore, the magnetism that the surface rocks show pertains only up to 20 km depth and not beyond. The mantle also cannot be the possible cause of the main geomagnetic field, but it plays a role in coupling the core with its property of electrical conductivity. It leaves therefore that core is the main source of Earth's magnetic field. The suitable internal motions of a large fluid conductor cause it to act as a self-exciting dynamo. The main reason for this is that the Earth has a fluid core, the chief constituent of which is iron. Further, the core is a good conductor of electricity and a fluid in which convective motions can take place. It permits both mechanical motions and a flow of electrical currents. The interaction of the mechanical motions and the flow of electrical currents generate a self-sustaining magnetic field. Under the dynamo theory, the secular variation can be explained from the reflecting eddies and changing patterns in the motions of the core. The reversal of the axial dipole field as evidenced in paleomagnetic observations may also be explained by assuming a series of coupled dynamos in place of a single dynamo. Rock magnetism. By means of magnetic surveys, we draw detailed conclusions about the magnetization of rocks within the Earth's crust and assume that this property is blindly related to the lithology of the subsurface. But in reality, the connection between a rock's geological properties and its magnetization is rarely simple, and it is, at the stage of our knowledge, impossible to lay down any strict rules upon which to show a relationship. Yet, the understanding of the magnetic properties of various rocks has helped in showing many geological complexities through magnetic surveys. In the past few decades, a considerable effort has been directed towards research in rock magnetism, mostly with a view to helping decide upon such large-scale geophysical and geological questions as whether or not continental drift and polar wandering have taken place. It is a well-known fact that the rocks are aggregates of minerals. They contain minor amounts of magnetic minerals that give a magnetic character to rocks. Every material possesses to some extent a kind of magnetic property. They may be diamagnetic, paramagnetic or ferromagnetic depending upon the mechanism causing the magnetic orientation within the rock. Those materials when placed in a magnetic field will acquire a small moment which is in a direction opposing the field are called diamagnetic. Examples of diamagnetic minerals are quartz, rock salt, feldspar and gypsum. Paramagnetic minerals are those when placed in a magnetic field, they acquire a magnetization which is proportional to and in the same direction as the external field. Examples are garnets, biotites, pyroxenes, olivines and amphiboles. If a rock has an appreciable magnetization, it is because of its ferromagnetic property, that is, a ferromagnetic material, and when placed in an external magnetic field, it acquires more magnetism. In ferromagnetic materials, interaction among the neighboring atoms is so strong that the magnetic moments of all atoms are apt to be parallel against the disturbing force owing to thermal agitation. If the total energy of the state wherein the spin of the electrons in the enclosed shells of the neighboring atoms is parallel, controlled chiefly by the exchange energy takes by minimum value, then the magnetic moments become parallel resulting in ferromagnetic character. From the consideration of Weiss molecular theory, there exists magnetization in spite of there being no external magnetic field. Examples for the ferromagnetic materials are magnetite, magnite and titanomagnetite. Ferromagnetic materials are further subdivided into ferromagnetic and antiferromagnetic depending on the spin moments of the neighboring atoms parallel or antiparallel.